Bismillah ar-Rahman ar-Rahim. In the name of God, the most gracious, the most merciful. Peace be upon you, God's blessings. This is Magid Kamil. I'm going to discuss practice problem 561, which is titled Bending Strength of Non-Compact Shapes. In practice problem 561, we have a non-compact W-shaped W12 by 65, which is used as a simply supported uniformly loaded beam with a span length of 50 feet and continuous lateral support. If the yield stress is 50 KSI and the author gives a relation between the life load and dead load, that the life load to the dead load is 3, it is required to compute the available strength and determine the maximum total surface load, or the summation of dead plus live loads in kips per foot. There are parts A and part B. For the first part, part A says to use the LRFD design. The second part, part B, requires an ASD design. First, we will solve part A, which is the LRFD design. If we refer to the practice problem 561, the data given shows continuous lateral support, which means that the spacing between bracing is equal to 0. We can write L sub B equal to 0. We have yield strength equals 50 KSI, and the ratio between live and dead load equal to 3, which means that L, capital L divided by capital D equal to 3. What are the parameters for local buckling? The parameters are BF over 2TF and H over TW, where BF is the flange width and TF is the flange thickness. At the same time, H over TW is the ratio between the height of the web to the thickness of the web. Based on the data that W12 by 65 is supposed to be non-compact section, we are going to check that through table 1.1 in the next slide image. Here is table 1.1. If we have sample F, which means that the section has exceeded the compact limit, we are expecting that W12 by 65 has sample F. Here is a sample F shape exceeds the compact limit for flexural with yield stress of 50 KSI. This table is based on the yield stress of 50 KSI. Suppose we use other than the yield stress of 50 KSI, for instance 36 or 65. In that case, the section will no longer be considered non-compact because the ratio will be compared to another value of lambda BF and lambda BR together with lambda BW and lambda RW. In the next slide, we will consider the second part of table 1.1 to get the values of B flange over 2T flange and H over T web, and also get the information regarding Z sub X and S sub X and radius of gyration R sub Y. We check here axis XX for S and Z values. The criteria of the compact sections are BF over 2TF, which is equal to 9.92, while H over TW is equal to 24.90. The value of Z sub X is 96.8 inch cubed, while S sub X, the elastic section modulus, is 87.9 inch cubed, and RY equal to 3.02 inches. We will move to the next slide. The graph is shown on the left side of the slide. It represents relation between lambda flange and the nominal strength M sub n. This is the value of lambda sub b. At the plastic range, we have the nominal strength equal to M plastic, which is equal to F yield multiplied by Z sub x, while at lambda r, we have M sub r equal to 0.7 F yield multiplied by S sub x. The horizontal part is from lambda equals 0 to lambda equals lambda b. The inclined line is for lambda bw to lambda rw. Then the inclined line joins M plastic and M sub r, and the elastic range for lambda of the flange is bigger than lambda r. The criteria of lambda sub b indicates that it equals 0.38 multiplied by the square root of E over F yield. The lambda r value of the flange equals 1 multiplied by the square root of E over square root of F yield. This is item 10 for section B. For the web, H over T W for the lambda sub B will be equal to 3.76 multiplied by the square root of E divided by F yield. While for lambda sub R for the web, it is equal to 5.7 multiplied by the square root of F divided by of E divided by F sub Y, which is item number 15 in section B. For both these items, we have F sub Y equals 50 KSI, and the E value is 29,000 KSI. The lambda B for the flange equals 0.38 multiplied by the square root of 29,000 divided by 50, which is equal to 9.15. The lambda R for the flange equals 1 multiplied by the square root of 29,000 divided by 50 equals 24.08. The lambda B of the web equals 3.76 multiplied by the square root of 29,000 divided by 50 equals 90.55. The lambda R for the web equals 5.7 multiplied by the square root of 29,000 over 50 equals 137.27. In the next slide, we have from table 1.1 for W 12 by 65, lambda F for the flange equals 9.92, which is bigger than 9.15, but is less than 24.08. This indicates that the flange part is an uncompact section. The lambda of the web equals 24.9, which is less than 90.55. The web is compact, but the whole section would be considered a non-compact shape for F yield equals 50 KSI. We estimate the product of Z sub x by F yield as equal to 50 by 96.8 equals 4,840 inch kips, while the product of 0.7 F yield by Sx equal to 0.7 by 50 by 87.9 equals 3076.5 inch kips. Divide by 12. The MP value equals 403 feet kips, while the MR 0.7 F yield Sx equals 256 feet kips. We expect that the nominal moment of the section will be less than MP, but bigger than 0.7 F yield Sx. A point on the inclined part of the graph represents a section. In the next slide image, we will get the value. The slope of the graph can be estimated as S equals the difference between M sub B and M sub R divided by the difference between lambda flange sub R minus lambda flange B, or equal to 4,840 minus 3,077 divided by 24.08 minus 9.15 equals 118.08. The section's M nominal value equals to MB minus S multiplied by lambda F minus lambda B equals 480 minus the slope value, which is 118.08 multiplied by open bracket 9.92 minus 9.15 equals 4,749 inch kips divided by 12 equals 396 foot kips, which is the nominal moment value for the LRFD design, multiplied by phi equals 0.9 by 396 equals 356 feet kips. In the next slide, we will refer to F sub 3 section, which is doubly symmetrical eye-shaped members of compact webs and non-compact cylinder flanges bent about their major axis. This is precisely our case, since the flange for W12 by 65 is non-compact while the web is compact. Only a few standard wide flange shapes have non-compact sections. When the F yield equals 50 ksi, we have 9 non-compact sections, starting from W21 by 48, W10 by 18, and W6 by 8.5. These sections have a ratio between M nominal and M plastic for each section that is less than 1. For instance, W21 by 48 is equal to the M nominal over M plastic equals to 99, while for W6 by 8.5 the ratio is 97%. According to the design example, our example, for W12 by 65, this ratio is 98%. We are going to check the M nominal, which we have estimated as 396 divided by the M plastic, which is 403, equals 98.2%, which is very close to 98%. We will move to the next slide section. I have taken this Excel sheet from the AICC sheet for the sections and introduced columns that represents modulus of elasticity as 29,000, F yield equals 50. I have listed the values of lambda for flange, BF over 2TF, and H over T web, and also lambda B for flange, and the values of Z sub X, S sub X, and R sub Y. I could expand this table for the estimation for data for lateral torsional buckling, L sub B, L sub R, and the relating M nominal. Later, we can include any metric section, and accordingly, I can get these values, L sub B and L sub R, from the graph, and we can prepare non-compact section for metric sections. In front of us is the table I have prepared, and I have extended from RY. I have introduced a J, CW, and HW, and all other factors to estimate L sub B and L sub R, as we can see. And this is L sub B, because of the screen is small, I cannot extend, but there is an item L sub R. Also, I have estimated the nominal and the M sub R. In the next slide, even though the bracing distance or the distance between bracing equals 0, then the M nominal should be equal to M plastic based on the lateral torsional buckling graph. But for our case of section W12 by 65, due to that non-compact section, the M nominal is less than M sub B. We need to adjust the graph by reducing MB value to a lesser value. We call it MB dash. We get the slope of the graph, and the LB value will be increased as we will see. The graph's x-axis represents the distance between bracing, while the y-axis represents the nominal plastic strength equal to F sub y by Z sub x for compact section. Compact section is from L sub B equal to 0 to L sub B equal to L sub B. But because we already have a nominal moment equals 396 feet Gibbs, we are going to adjust the graph by considering this value. So there is a drop here. This value M sub R is represented by 0.7 F yield multiplied by S sub X, which we have estimated earlier. Here we have 403 and 256, and the difference in X equals L sub R minus L sub B. The 403 represents M plastic, and 256 represents the M sub R. For L sub B, it's equal to 1.76 multiplied by R sub Y by the square root of E divided by F sub Y, can be estimated as 1.76 multiplied by R sub Y, which is equal to 3.05 by the square root of 29,000 over 50, equals 128 inches divided by 12 to convert it to feet. It would be equal to 10.66 and can be rounded to 10.7 feet, while L sub R value equals 35.01 feet from table 3.2 or by manual calculation. We can estimate the slope or PF value to be equal to 403 minus 256 divided by 35.01 minus 10.7 equals 6.02. Then the modified length LB dash would be equal to LB plus MP minus M nominal divided by BF. Then we can write 10.7 plus 403 minus 396 divided by 6.02 equals 11.86 feet, that we rounded to 11.9 feet. We will move to the next slide. We could confirm our answer by checking table 3.2 and getting the value of phi by MB, which is equal to 0.9 multiplied by 396 equals 356 feet Gibbs, which matches the value in the table. On the other hand, L sub B equals 11.9 feet, which is the same as the new LB value of 11.9 in the table. For the first equation, W ultimate equal to, we take D as a common factor, open bracket, multiply by 1.2 plus L over D by 1.6. Since L over D equals to 3, then we can rewrite the W ultimate as equal to D open bracket 1.2 plus 3 multiplied by 1.6, all equals to 6 multiplied by D which is bigger than 1.4 D. We can represent the beam as simply supported beam with a length equal to 50 kips and uniform ultimate load of 6 D. We will estimate the moment M ultimate equal to W ultimate L squared over 8. We take the value 6D multiplied by L squared divided by 8. This value M ultimate is supposed to be smaller or equal to 3 multiplied by M nominal, which is equal to 356 feet kips. We solve for the D value, which would be equal to 0.19 kip per foot, multiply by 3 to get the L value. The surface load equals 0.19 plus 0.57 equals 0.76 kips per foot. The surface load, this is the surface load based on the LRFD value that was required estimation based on option A. We will proceed to the ASD part B side. The value of M nominal is equal to 396 feet kips. Similar to the process we did earlier, we divide by the lambda sub B. Lambda sub B is 1.67. We are going to multiply 1 over 1.67 by 9396 equal to 237 feet kips. This value, we are going to check it through table 3.2. This is table 3.2. M sub B over omega B equal to 237 feet kips, and L sub B equals to 11.9 feet. As we remember, our estimated LB is 11.9 feet. On the last slide, the W total, because we are designing according to the ASD, equals W dead plus W live. The dead plus live equals to capital D plus 3D equals 4D. We are going to represent the beam as simply supported beam with a total W equal to 4D. The span is 50 feet. The M total is W total by L squared divided by 8, supposed to be less or equal to M nominal over omega B. We have it already as 237 feet kips. We are going to equate M total equal to 4D by 50 squared divided by 8. We will get the D value equals 0.1896. The life load is value is equal to 3D, where D is the dead load. We get 0.5688 kip per foot. Adding dead plus life together, we are going to get the surface load, which will be equal to 0.758 kips per foot. This is the end of our discussion of practice problem 561 after solving part B design using ASD design. Thanks a lot. God bless you all and goodbye.